Hello, guys. Welcome back to Men's on African Motives. Still working on industrial electronics N3, working on revisions on question papers. So in this case, we are going to be focusing on the question paper of April 2021 that has got DC and AC theory that we are going to be focusing from this question two. We've got a lot of things that we are going to learn from this video. There is a lot, I promise, that you're going to have because it has a lot of questions and you can learn a lot from there. All right, so without wasting much time, question number 2, we are given fig 1 shows a series parallel circuit. Use Kirchhoff's law to answer the questions. All right, so this is the diagram that you are given on fig 1 from A, B, C, D, E up to F. All right, so we are given the loops, the loop 1 and the loop 2. Okay, so this is the first part of the question. We are given on 2.11 to determine the equation for loop 1, and we are given it as A, B, E, F, A, which is loop 1 in this case. So this is A, B, E, F back to A. All right, so this is the loop that we are going to be focusing. So I'm just going to take up to this part here. So if we are to check from our loop 1, all right, so this is what we have. So this is 2.11, which is given as A, B, E, F, A, all right. So if we are to consider this part, checking the flow of current from the positive, this is our negative. So the current is flowing in this direction of I1 with the arrow the way that is given. So the first branch, we are given current I1. Then from B to E, we are given a current I2 flowing in the same direction of the arrow that we are having. All right, so we know that the voltage, which is the total voltage, is equal to the algebraic sum of the voltage drops across that in this closed loop that we have. So which means VT is equal to the voltage drop, which is from E to F to A to D. There is current I1 from this point E, F, A up to B. We have got current I1, which is affected by the resistor R1. This is the only resistor that we have. If we move on to the other branch, which B to E, we have got current I2. So this is going to be plus current I2 times the resistor that is affected in this branch, which is resistor 2. So this is what we have from loop 1. So we are going to insert our values. Our V, which is the total voltage of 24, is equal to I1 times R1. We've got R1, which is 680. So that is 680 I1 plus, we are still in the same path. There's going to be a positive 330. So this is 330 times current 2. So this is the equation that we are going to have from this loop. All right, so we are done in this part. We move on to the other part of the question, which is to determine the equation for loop 2, which is given as this part that is 2 marks again, which is our loop 2. This is the bigger part that we are having, the outer part of our circuit in this case. So from this part, that is from point A to B to C to D to E to F to back to the point A. So this is the you are following the outer part of your diagram. This is the outer part of your diagram. All right, so this is what you're going to have. This is 2.12. So if we are to check in this outer part, which is our loop 2, we have got a voltage source from the positive, which is V, being equal to, remember, we are going to have the voltage drops. So from the part of E to F to A to B, we still have the same condition with I1 and R1. So we are going to have the product of I1, R1. We move from the, remember, we are following from B to C to D. This is the same branch from this point B, C, going this direction up to the point E. We are having the same current in this branch, which is I1 plus I2. So this is the current that we are going to use in this case, which is the current I1 plus I2 flowing in the same direction. So we're going to use plus current I1 plus current 2 in this case times the resistance in this route from B to C to D. We have got two resistors, R3 and R4. So we're going to add these two together. That's R3 plus R4. All right, so that's what you're going to have in this case, which is the total voltage of 24 is equivalent to I1 times R1, which is R1, that's 680. So you've got 680 I1 plus R3 plus R4. We are going to add R3, 560. So this is 560 plus R4, which is 680. All right, whatever that you're going to have, we multiply to I1 plus I2 like this. All right, so this is going to be 24 is equal to 680 I1 plus, if we to combine 560 and 680, this is going to give us 1,440 into I1 plus I2 in this case. So we can expand the bracket so that we can collect our like terms. That's I1 plus 140, 1,240 I1 plus times I2, that's 1,240 I2. Then we can collect like terms with the 680 I1 and 140 I2 in this case, so that we can simplify further. All right, so what are you going to have at the end? This is going to give us, if we simplify properly, 24 is equal to 680 plus 1,240, we're going to have 1,920 I1 plus 1,240 I2 like this. All right, so this is what we are going to have on our second equation, or the second part, which is from loop 2 in this case. All right, so these are the typical questions that you'll be given. On the other part, now you're given to determine the values of I1 and I2 by using equations in question 2.11 and 2.12, which means we're going to apply the equations that you obtain. The first equation, you write your equation, this one, that's our first equation. Then the second equation, this one. All right, so I'm just going to write these equations down. So remember, we obtained from the first part, so this is 2.13, the first equation, we got 680 I1 plus 330 I2, which is equal to 24. Then the second equation, we got 1,920 I1 plus 1,240 I2, which was equal to 24 again. So these are the two equations that we had, our first equation and our second equation. So we can actually solve this by eliminating any part depending with which part you want to work from. Okay, so in this case, if I am to find I1, therefore, I'm going to eliminate I2. So I'm going to eliminate I2 in this case. So to eliminate I2, I focus with this part with I2. That is, I interchange these values, multiply on top, the top part, which is equation 1 by 1,240. Equation 2, you multiply by 330. So we are going to multiply. Okay, so let me do this so that you can properly see what I'm trying to say here. All right, so this is 2.13. So on top here, we are going to multiply by 1,000. Since we are focusing on I2, so we interchange the ones for I2, all right, the values for I2. So once 1,240, then below, which is the second equation, we multiply by 330 in this case. But these values can be reduced. So what you do is that you can simplify this from your calculator. So let me show you what you're going to do. So from your calculator, you are going to simplify this as, these are the values that you are given, which is 1,240 and 330. So you can divide them, 1,240 like this, divided to 330, so that you see, can it be reduced? So this can be reduced to 124 over 33. So the 124 over 33 is the one that you're going to use in this case, meaning to say we are going to multiply on top by 124. Instead of this, we are going to multiply by 124. Here we are going to multiply by 33. So we are no longer using these values. We are using the reduced values now. So this is going to multiply everything from the given equations. All right, so that is the condition that you're going to have. So it's 124 times 680, which is going to give us 84,000. So that's 84,320 I1. All right. We move on to 124 times 330, which is going to be 40,920 I2 is equal to 124 times 24 in this case, that is 2,976. We are done. So this part multiplies everything from equation 1. Same with 33. 33 is going to multiply everything in equation 2. That is 33 times 1,920, which is going to give us 63,360 I1. Then is 33 times 1,240, which is going to give us 40,920 I2 in this case. This is equal to 33 times 24, which is 729. So from the two equations that we have, we can see that the part of I2 and I2, they are the same. This is 40,920, 40,920. So you eliminate I2. If these two signs are the same, I told you guys that you subtract. Whether it's a minus and a minus, as long the signs are the same, you subtract to eliminate. So we have a plus and a plus. So we are going to subtract to eliminate. So we're going to subtract equation 2 from equation 1. That's equation 1 minus equation 2. All right, so let's see what you're going to obtain from this part. From current 1 and current 1, if we subtract these two, we are going to obtain 20,960 I1. Then on I2, we are eliminating. This is going to give us a 0. So that means we are left with nothing in this case. So on the other side of the equation, we subtract 2,976 minus 792. This is going to be 2,184. So we can divide both sides of the equation so that we can determine the value of I1 by 20,960, both sides by 20,960. We can have the value of I1. So that is the current flowing through I1 in this case, through the circuit. That is our I1 in this case, which is going to be something like 0,10419 and so forth. So this is going to be 14. All right, we can have this as it is, or you can write it in milliamps, whatever way that is best with you, or that you feel is you are capable of using. All right, so this is our current I1. So with this current, we can substitute with any to any part of the equation from these two equations that we had. That is, we can substitute any equation that you pick in this case. So I'm going to take this first equation of 680 I1 plus 330 I2, which is equal to 24. Then I substitute the value of I1 that I got here. Remember that I've got I1 in this case. So meaning to say from equation 1, so from equation 1. So from equation 1, we were given as 680 I1 plus 330 I2, which was equal to 24. We can substitute the value of I1 that we got. So this is going to be 680 times I1, which is 0,104 plus 330 I2 is equal to 24. So from there, we can solve for I2. Depending with your simplification, you can combine the two, or you can transpose this part as it is to the other part of the equation so that we can subtract at the end, we divide. So this is going to be 330 I2 is equal to 24 minus this product, or the answer that you're going to have depending with your simplification, which is 0,104. All right, so this is 0.4 in this case. So everything can be divided by 330 so that we can have the value of I2 in this case. So from this part, if we divide everything properly, 24 minus 64, where am I having this? It's 680. Where am I having the 64? This is 680 times 0,104. All right, so if we are to do this, this is going to give us negative, that was negative 0,142 if you round off to 2 decimal places. All right, so this is what you are going to 3 decimal places. This is what you're going to have in this case. All right, So the negative is just for the direction part that you are taking, but it does not even affect us at all. So these are the currents that we're being asked to calculate from this part, all this part, from the equations that you had before. You work from those given equations so that you can solve for the other part that you're given. All right, so this is the first part of the question. On the other part, like I said, this question paper had a lot. On 2.2, we are given on the part of Kirchhoff's laws, again, to apply or to use the Kirchhoff's current law to answer the questions. All right, determine the equation for IY. We're given to determine the equation for IY from this part that we are given, and this is 2 marks. Okay, so this is what we have. We are given the total current. So this is a positive, negative. So this is the flow of current, your total current. It branches at this point into I2, into I3, into IX, into I1. So these are from the total current that we had. It is the one that is branching into these currents. Then these currents, I2 from this branch is going to this branch. I3 also in this branch, they meet at this point, they branch into another current, which is IY in this case. So which means IY is taken from this branch here, from I2 and I3. These two, they meet at this point. They are flowing towards the junction, and this is flowing away from the junction. So that means 2.21 current IY is equal to current I2 plus current 3. So this is going to be current 2 plus current 3. All right, so that is the consideration of the question. Then we move on to the other part, determine the equation for IX. IX, we can see that we have got IX from this branch here. So we can trace back where this IX was taken from. Remember what I said, IT is the total current, is the one that branches giving these currents, I2, all these currents here, they are a total of this current IT. So meaning to say, we can have the value for this current, which is IX, taken from the total current. So it is going to be the total current in this case, minus these other currents, which is we are going to subtract current 1, we subtract current 2, we subtract current 3, so that we can remain with the current IX. So we are going to subtract these currents from IT, which means we are going to subtract current 1, we subtract current 2, we subtract with current 3 combined together. So this is going to be the equation for IX, all right? Or you can expand the minus I1 minus I2 minus I3 if you expand the bracket, all right? So this is the equation that you can have. We move on to the other part of the question, which was on AC theory. Now we are given fig 3, which shows a series RCL, which is an RLC circuit, with the given inductance of 66 millihenries, the resistance of 75 kilo ohms, the capacitance of 530 picofarads, and the voltage source being at 120 and the frequency at 60 kilohertz. So from this circuit diagram that we are given 2.31 to calculate the inductive reactance, which is XL in this case. So from the diagram that we are given, we have got inductance L, so you can calculate the inductive reactance. So this is 2.31. So remember that XL, we can take it from our formula. XL is equivalent to 2 pi FL. So this is just direct substitution into the formula, 2 pi times the frequency, which is our frequency, it's 60 kilohertz. So it's kilo, that's times 10 to the exponent of 3, times the inductance, which is 66 millihenries. So this is 66 times 10 to the exponent of minus 3. That's milli to the exponent of minus 3. So we can determine the value of the inductance, which is going to give of XL, which is going to be 24881,414 in ohms, right? Or we can even write this in kilo ohms, which is which can be something like 24 5.881 in kilo ohms. All right, that is if you are to write in kilo ohms. All right, we move on to the other part of the question. We are now given to calculate or to determine the capacitive reactance. Again, 1 mark. Capacitive reactance, that is our XC. So you can even take from the formula. This one is a direct application of the formula. We know that XC, so this is 2.3. 2, that's XC is equal to 1 over 2 pi FC. So you can substitute our values. That's 1 over 2 pi times the frequency, which is at 60 kilohertz, 60 times 10 to the exponent of 3, times the capacitance, which is 530 picofarads, means to the exponent of minus 12. That's picofarads. So we're going to have our XC from there, which is our XC is going to give us 5,004,872 ohms. All right, or you can write it in kilo ohms, which is going to be 5, something like approximately something like 5.005 kilo ohms. If you are to write in what? In kilo ohms, it's going to be 5.005 kilo ohms. All right, so that is what we had in this case. Then we move on to the other part of the question, which is to calculate the total impedance of the circuit, which is on 2.33, to calculate the total impedance of the circuit. So the total impedance of the circuit is taken from XC and XL in a series circuit like this. So you compare the two that you have determined here. We have got XC and XL. So the formula is formulated from the two that you have. You compare which one is bigger, the XL or the XC in this case. XL is 24,000, which is and 5,000 for XC. So you can see that XL in this case is greater than or is bigger than XC. So on a condition that XL is greater than or XL is bigger than XC, that means our total impedance Z, which is the phasor sum of the resistances, it is going to be R squared plus you subtract these two, that is XL, the bigger one, minus the smaller one, that is XL minus XC. But in any case, maybe you vice versa these ones, it is not going to affect your answer anyhow or anyway. So our RS, the resistance, which is given a resistance of 75 kilo ohms. Kilo, that's 1,000, so that's 75,000 kilo ohms. So this is going to be 75,000 squared plus the difference between XL and XC. So our XL, remember, is 24,881, 414. Then we subtract our XC. In this case, we determined or we got the value for XC, which was 5,000. That was 5,004, 872. So everything that we have, we square it. So this is going to give us the total impedance of the circuit in this case. All right, so from these values that we have, our Z being the total impedance is going to be, okay, so this is going to be something like 5, 8, 9, and so forth. So, or you can even write it in kilo ohms like that. So you can have it divide by 1,000. So it's going to be in kilo ohms. All right. Okay. So you can even write it in kilo ohms from the values that we have, or you can even use these values in kilo ohms. These are smaller values. You can use the smaller values than to use the bigger ones because we are going to have a lot of things there. On 2.34, we are now asked to calculate the total current of the circuit from the information that we have, the total current. Since we have got the total impedance, or we've got our total impedance, which is Z in this case, we can calculate because we have also the voltage in this case. So remember that current is equal to voltage over the impedance that we got in this case. So that means we can have our total current. So this is 2.34. So the total current is going to be voltage over the total impedance, which is the voltage of 120 over the total impedance that we got in this case. Remember, our Z is 77,589 kilo ohms. So we are going to have this with kilo, which is to the exponent of what? To the exponent of 3. So this is going to be 77,589 times 10 to the exponent of 3. So we're going to have the total current from there. So the total current, we are going to obtain something like 0.00155 466 and so on. So if we round off, or if we convert to milliamps, just to make sense, guys, we multiply by 1000, we're going to have 1,545. This is going to change this one into a 5 in milliamps. All right, so this is what you're going to have in this case. So this is the total current. Then from there, we are given to calculate the voltage across the capacitor on 2.35, the voltage across the capacitor. So since we know that this is a series circuit, and in a series circuit, the current is the same. So which means the total current that we see here is going to affect everything. We are going to have the same current flowing of 1.545 milliamps. So if we have got a current and the inductive reactance, we can have the voltage. If we have got current and resistance, we can have voltage. So it is the same part that we are going to apply on this part to calculate the voltage across the capacitor. We are going to use the total current and the capacitive reactance that we got in this case. We have got our capacitive reactance here. So this is going to be 2.35. So VC, which is the voltage across the capacitor, is going to be total current times, so we are going to use the total current times the a capacitive reactance in this case, which is the total current is not going to change, guys. This is our total current, 1,545 milliamps. So we're going to have this as VC is 1,545 milli. That's times 10 to the exponent of minus 3 times XC, which is our X is this value, or you can just write it as 5,005 or just zeros. Okay, just any value that you have, 5 to the exponent of what? To the exponent of 3, this one. Or you can use this one. It's just going to be an approximated value that you're going to have. All right. So our VC is going to be 7,733 volts. All right. So that is what you're going to have the voltage across the capacitor. Use the total current that you have because it's a series circuit and current is the same. So it is the same thing with 2.36 where we are calculating the voltage across the inductor. In this case, it is the same because the current is the same. All we need is our inductive reactance, which is this XL. So we are going to use current and XL in this case. So that's 2.36. So we are going to have the voltage across the inductor as the total current times the inductive reactance, which is the total current still is not changing, 1,545 times 10 to the exponent of minus 3. Use this time using our inductive reactance, which is 24,881 kilo ohms. So it's going to be 24,881 kilo ohms. That's 24,881 times 10 to the exponent of 3. So you're going to have the voltage across the inductor, which is going to be 38,441 volts in this case. All right, so that was the idea of the question in this case. This is how we can attempt such a typical question. The other part, we are now asked to calculate the phase angle, and that is 1 mark for that. All right, so how can we calculate the phase angle in an RLC series circuit if you're given an RLC series circuit in this case? All right, so our phase angle can be taken from so many formulas. In this case, we can have our phase angle, which is referred to as theta, as the arc cos. So this is going to be the arc cos of resistance over the total impedance. Or we can have this as arctan, as theta is equal to, we can have this as theta is equal to arctan. We subtract XL minus XC over the resistance, like that. All right, so this is what we can have. So I'm going to just use this one. So our theta is going to be equal to arc cos resistance, which is the resistance of the circuit, which is the one that we are given from our circuit. Our resistance is 75 kilo ohms. So that is 75 kilo ohms. So 75 times 10 to the exponent of 3 over the total impedance, which is our Z. Remember, we calculated Z here. We got 77,589 kilo ohms. So this is what you are going to use, which is 77,589 times 10 to the exponent of 3. So we can obtain the value of theta in this case, which is 14,843 degrees. All right, so that is our phase angle in this case. All right. So these are the typical questions. You have to be very, very careful. Then the last part of the question, 2.38, is to calculate the resonant frequency in this case. Let's say this circuit is at resonant. What is going to be our resonant frequency? So that is what the question is all about. So I can just remove this part. We no longer need this. All right. So the resonant frequency can be taken from the formula. All right. So let's see the formula. So this is 2.38. So remember that the resonant frequency is equivalent to 1 over 2 pi square root of LC. Also, we are given this formula in our formula sheet. So we are going to just substitute, that is 1 over 2 pi times the square root of L, which is our inductance, 66 times 10 to the exponent of minus 3, that's millihenries, times the capacitance in this case, which is 530 picofarads, that's times 10 to the exponent of minus 12. So this is what we are going to have as our resonant frequency, which is measured in what? In hertz in this case. So this is going to give us 26909,785 in hertz, like that. Or we can have this in kilo hertz. If we divide by 1,000, this is going to be 26,909, but this 7 is going to change this 9 into a 10. This one gives a 1, so it's going to be 9,1 in kilohertz. All right, so this is what we are going to have at the end in this case. So you have to be very, very careful, guys, in your simplification, whatever that you're given. So that was the last part of the question, which is on 2.3 to calculate the resonant frequency, having a total of 2 marks, and everything on this question was actually 25 marks. So this is how we are supposed to answer these questions. So it's very, very important that you work with past exam papers so that you can trace how do they give these questions and how are you supposed to attempt such typical questions. But for now, that's what we had, guys, from Resonant African Motives, working on industrial electronics N3. Till we meet again.